Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit 1, Lesson number 9 on exponential and logarithmic basics. Like most lessons in this introductory unit, we assume going in here that you've had already work with exponential expressions and logarithmic expressions. If that's not the case, you would be better served with perhaps a lesson or video from our earlier course in Algebra 1, or eventually in our course from Algebra 2. But for now, let's jump into some exponential work. All right, exercise number 1, very simple. It just says, evaluate the expression 4 to the x for the following values of x without using your calculator. Since we've already done since we've already done a lesson on exponent review, what I'd like you to do is pause the video now and make an attempt at this. All right, well, let's go through it. I mean, it's simple enough. What we're going to do in each case is just substitute x into this expression and see what we get. Right, so in this case, we get 4 to the third. Obviously, that's 4 times 4 times 4. That's 16 times 4, and that's 64. I wouldn't expect most of my students to write all that out. Probably just go from 4 to the third to 64 automatically. In letter B, we have 4 to the negative 2. Remember, negative exponents mean that you are going to repeatedly divide the number 1, right, by 4 here, so we're going to have 1/16. X to the 1/2, x equals 1/2. That means we have 4 to the 1/2, which means we have the square root of 4. Keep in mind, this is only positive 2. It's not negative 2. All right, there's no negative out front. If I wanted the negative square root of 4, I would have to have something like this. All right, but that's not what I have here. All right, finally, x to the negative 3/2, x equals negative 3/2. We're going to have 4 to the negative 3/2, which by definition is 1 divided by 4 to the 3/2, which again is 1 divided by the square root of 4, quantity cubed, and that's going to be 1 divided by 2 cubed, and that's going to be 1/8. Now really, I put in this exercise number 1, specifically so that you can answer exercise number 2. So take a look. Is there any real value of x that can make 4 to the x equal to 0? Why or why not? Can 4 to the x be negative? Pause the video now and consider these questions. All right, well, let's talk about them. There's a whole lot of no in terms of this question. Is there any real value of x that can make 4 to the x equal to 0? And the answer is no, right? And it's very simple, right? If we have 4 to the a, right, where a is positive, clearly the result is positive, right? If we have 4 to the negative a, that's just 1 divided by 4 to the a. And again, assuming that a is positive, so negative a is negative, that's going to be a positive divided by a positive. That's still going to be a positive, right? And look at that from exercise number 1. In exercise number 1, we took the number 4 and we raised it to the third, to the negative 2, to the 1/2, to the negative 3/2. We raised it to every type of number except an irrational number, and that is admittedly a little weird. You know, what is 4 to the pi or 4 to the square root of 2? But regardless, it's not going to be equal to 0. Right? Any positive number raised to a power will be a positive number, assuming that power is a real number. You can actually get negatives, but you have to go into the complex realm, into realms with i's. So let's not worry about that. Can 4 to the x be negative? Absolutely not. No, definitely not. Again, it can't even be 0, then it certainly can't be negative. Now this is very important. When we work with exponential expressions, the base of the expression is always a constant, and on top of that, it's always a positive constant. And the fact that those expressions are always greater than 0, not equal to 0, not less than 0, is actually quite important. All right, pause the video now and write down anything you need to. Okay, I'm going to clear out the text. Let's move on. Now, there aren't a lot of algebraic techniques that deal with exponential equations where you don't have to use a calculator. All right, notice what I just said. There are algebraic techniques involving logarithms, and we're going to get into them in a little bit. But without bringing a calculator into it, the only real method that deals with exponential equations is called the method of common bases. Method of common bases. And it's actually really quite neat and pretty easy for people. We look at this exponential expression equal to this exponential expression. And what we hope we can do is find a common base, right? So think about it. Here we certainly can. We can find a base of 2. So 4 is the same as 2 squared, right? And then to the x. 1/8 is the same as 2 to the minus 3. Sorry about the different ways my 2's look there. To the x plus 10. Now, we've got that exponent law that says if I have x to the a raised to the b, that's x to the a times b, right? Well, we're going to apply that right here. We've got 2 to the 2x is equal to 2 to the negative 3x minus 30. Make sure that you distribute, right? Now the beautiful thing is we can state the obvious. If 2 to the 2x is equal to 2 to the negative 3x minus 30, well, then 2x must be equal to negative 3x minus 30. 5x must be equal to negative 30, and x must be equal to negative 6. Now I want to be very clear about what I'm not doing. I am not canceling out the 2's. I'm not dividing by 2 on both sides. Even if I did, I wouldn't cancel out the 2's because I'm not multiplying. I'm exponentiating. In this case, I'm just recognizing the fact that if I've got the same base on either side of the equation, then their exponents must also be equal. Now that really gets into the fact that exponential functions are one-to-one, and we haven't even reviewed that yet. So we're kind of getting a little bit ahead of ourselves, but I think that's okay. So pause the video now and see if you can work through that quadratic equation in letter B. All right, let's go through it. I'm going to use my eraser. I'm going to try to use my eraser to get rid of this a bit. We're still going to need that principle, but let's do it. So here the common base is going to be 3, right? So I can write 9 as 3 squared, then to the x squared minus 3x, and I can write 27 as 3 cubed, then to the x plus 6. Always guess, if you have to, on the base with something low. Distribute that 2x squared minus 6x, distribute that 3x plus 18. Once we have the bases the same, and of course that's absolutely key. If the bases aren't the same, then you cannot set the powers to be the same. But once those bases are the same, then we can drop them. We're not canceling them, we're just recognizing, that those two exponents would have to be equal. And now we're off and running. We could use any method we really like here to solve this quadratic. We could use completing the square, the quadratic formula. I'm going to be always biased towards factoring. 2x, x, what do you think? So 3, 6, 6, 3, yeah, I like it. 6, 3, negative, positive, right? Negative 12, positive 3 is negative 9. So x is negative 3/2, and x is positive 6. Of course, we can always go back and check these. The 6 wouldn't be terrible. The negative 3/2 would be a little bit more rough to check. Neither one of them are extraneous. Extraneous roots don't tend to come up with exponential equations, although they sometimes do come up with their inverses, which are logarithmic equations. All right, pause the video now and copy down anything you need to before I scrub out the text. All right, here we go. Scrubbing, moving on. So now we move into logarithms. And logarithms are very strange. So before we even get into this exercise, let me just talk a little bit about logarithms. Logarithms are the inverse of exponential functions, and I think of them very similar to the way I think of square roots. In other words, right now, most students at this level know that the square root of 25 is 5, right? But if you were asked why, right, you would probably say, well, because 5 squared is 25, right? And it's interesting because that means that we have to actually appeal to the squaring function in order to justify the square root function or operator, depending on what term you want to use. All right, logarithms are the same way. Let me just clear that out. When I take the log base 2 of 32, what I'm really trying to answer is this question. 2 raised to what power is 32, right? I'm trying to figure out n. And in this case, n is equal to 5. So the log base 2 of 32 is 5. Why? Well, because 2 to the 5th is 32. All right, but still, log base 2 of 32 is 5. Make no doubt about it. Given all that, see if you can do B, C, and D without using your calculator. All right, well, let's go through them. Well, the log base 4 of 1/16 is negative 2. Why? Because 4 to the negative 2, which is 1 over 4 squared, is 1/16. All right, 1/16. So that's kind of cool, right? Again, it's a little backwards because you're thinking about the exponential function and not the logarithmic function. Now, letter C, this is kind of weird. It's like I forgot to write what the base is. All right, that's what's called the common log. Okay, and the common log is always base 10. Base 10. Let me do this. Seems to be getting in my way a little bit. So really, I'm saying, what is the log base 10 of 1,000? Hopefully, you said 3. Again, that's my answer. This is just my explanation. Why? Because 10 to the 3rd is 1,000. All right. Now this one, a lot of people will call the ln or the ln. It's called the natural log. And it is base e, natural log. So really, this is the same as log base e of the square root of e. Now, if you remember, e is an irrational number. It's approximately 2.71, and then it goes on forever because it's irrational. We don't really need to know that so much, but we do need to know that the natural logarithm has a base of e. So this is kind of cool because that means the natural log of square root of e is 1/2. It's almost a silly reason, right? When we write out our y, well, it's because e to the 1/2 is the square root of e. That's it. It's the whole thing. All right, so write down whatever you need to, and then we'll move on and do some more work with logarithms and exponentials. Okay, let me clear it out. And let's keep going. All right, exercise 5. All right, given the function y equals 5 times the log base 2 of x plus 1 minus 15, find the following algebraically: the function's y-intercept and the function's x-intercept. And again, we want to do that algebraically. We could probably do it graphically given the operating systems on most modern graphing calculators, but we want to do it algebraically. Now, I have no doubt that everyone should be able to do letter A on their own. Letter B might be a bit trickier. What I'd like you to do is pause the video now, take a shot at both of them, twist my tongue, and then we'll revisit, okay? All right, let's go through them. Well, a function's y-intercept, as you've learned from previous years, is always where x is equal to 0. So figuring out the y-intercept, is equivalent to evaluating this. All right, well, but what do we have? We have 5 times the log base 2 of 1 minus 15. Now, know your order of operations. This comes first, right? This multiplication comes second, and this subtraction comes third. I'm not solving an equation. I'm not trying to undo those. That'll come next. But what I do want to do is make sure that I evaluate all this properly. Now, the real trick here is the log base 2 of 1, and that is equal to 0, right? 2 to the 0 is equal to 1. So y is equal to 5, 5 times 0, right, minus 15, and that's negative 15. Watch out. It's not necessarily that number that's just added on. This happened because of that plus 1 in there. Okay, let's talk about the function's x-intercept. Well, that occurs when y is equal to 0. So let's set that up. 5 times the log base 2 of x plus 1 minus 15. Now this is one of those scenarios where the variable we're solving for shows up only once. And due to that, we can just undo what has been done to the variable. So let's talk about what's been done, right? The first thing that was done is we added 1. Second thing that was done was that we found the log base 2 of it. The third thing we did was we multiplied by 5, and the fourth thing that we did was subtract 15. So we're going to undo that in the opposite order. So we're going to add 15 to both sides. Right, that takes care of that. Then we're going to divide by 5 on both sides. That takes care of that. Now the question is, well, how do we undo the logarithm? We always have to apply the inverse of whatever's been done. So we add to invert the subtraction. We divide to invert the multiplication. And we exponentiate base 2 to get rid of a log base 2. Those literally cancel each other out. 2 to the third is 8. And then we subtract 1 from both sides. And our x-intercept is x equals 7. Now, a lot of people get confused. Why would these two cancel out? Well, partly it's just due to the definition of what a log is. A log is the inverse of exponentials of the same base. You could think about it, though, real hard, right? This gives as an output what you have to raise 2 to in order to get x plus 1. Think about that for a minute. Forget about this 2. Just think about this. It gives, as an output, what you have to raise the number 2 to in order to get x plus 1. But if we take 2 and we raise it to the number that we have to raise 2 to, that sounds weird, in order to get x plus 1, we have to get x plus 1. Right? As I tell my students, if I carry out the action that will result in putting a cat in the box, then I'll have a cat in the box. Right? If I take 2 and I raise it to the number I have to raise 2 to in order to get x plus 1, I get x plus 1. That's what I get. All right, well, I'm going to clear out the text. So pause the video now and write down anything you need to. Okay, let's do it. Let's clear, adjust the glasses, and keep going. All right, exercise 6. Solve each of the following logarithmic equations for all values of x. Be sure to check your answers for any extraneous roots. No. All right, so this is exactly what we did in part B of the last problem. Why don't you go ahead and do that, and then we'll talk about our results. All right, let's go through them. So in the first one, we've taken x, added 3, taken the log, subtracted 2. So undo it by first adding 2 to both sides, giving me the log base 5 of x plus 3 is equal to 2. Get rid of the log base 5 by exponentiating on both sides, base 5. We get x plus 3 is equal to 25. Please note it's 5 squared, not 2 to the 5th. Subtract 3 from both sides, and we get 22. Easy to check, by the way, log base 5 of 22 plus 3 minus 2 equals 0. Log base 5 of 25 minus 2 equals 0. Log base 5 of 25 is 2. 2 minus 2 equals 0. Check. All right. How about letter B? What did we have here? Let's go back to that. What do we have for letter B? So we had x multiplied by 6, subtracted 1, then the logarithm, then multiplication. So we'll have to get rid of that multiplication by first dividing. We'll get rid of the log base 9 by exponentiating on both sides, base 9. Now 9 to the 1/2, well that's 3, right? That's just equal to the square root of 9, which is 3. Not plus or minus 3, just 3. Then of course we get 6x equals 4, and x equals 4/6, or 2/3. Again, fairly easy to check. 2 times the log base 9 of 6 times, watch this, I'm going to even use the 4/6 just to make the cancellation easier. Cancel. right? So now we have 2 times log base 9 of 3, right? 4 minus 1 equals 1. Log base 9 of 3, what do you have to raise 9 to get the third? That will be 1/2. And 2 times 1/2 equals 1. That checks. So no extraneous roots here. But they can arise in logarithmic equations, so it never hurts to check. All right, I'm going to clear out the text, so pause the video now if you need to. Okay, here we go. Excellent. Let's move on and do one last problem. Agronomists have modeled the height of a corn plant t days after it was planted using the natural logarithm and the equation h equals 25 times the natural log of expression t plus 8 divided by 14, where h is measured in inches. So t is the number of days, h is the number of inches. Letter A, for what value of t does this equation predict that h is equal to 0? The height is equal to 0. All right, so we have to solve this equation. All right, so to solve that equation, again, we just need to undo what's been done to t. Let's see, we had t, we added 8, we divided by 14, took the natural log and multiplied by 25. So first thing I'm going to do is get rid of the 25. 0 equals the natural log of t plus 8 divided by 14. Right, I need to get rid of the natural log now by exponentiating both sides. E to the 0 is 1. So I'll get 1 equals t plus 8 divided by 14. Now I get t plus 8 equals 14, and t equals 6. So apparently it took us 6 days for the plant to even reach a height of 0. That's what's called the germination time, how much time it takes for the plant to germinate. Letter B, to the nearest tenth of a day, how long will it take for the corn plant to reach 2 feet in height? All right, well, why don't you pause the video now and see if you can solve this problem on your own. All right, let's go through it. Well, if we're 2 feet high, we don't want to put in 2 for h because h is measured in inches. So, of course, 2 feet is the same as 24 inches. And we have 25 here, ln at t plus 8 divided by 14. All right, we've added 8, we've divided by 14, we've taken the natural log and then multiplied by 25. So that's the first thing I'm going to get rid of. I'm not going to evaluate that as a decimal, we'll just leave it as 24/25. So we have 24/25 equals the natural log of t plus 8 divided by 14. Need to get rid of the natural log, so I'll exponentiate on both sides. That cancels. This I'd have to just work out. Now, I think I'm going to leave it like that for a minute, okay, and try to keep working through it. I'm going to multiply by 14 on both sides, and then I'm going to subtract 8. So a nice, beautiful, exact answer is 14 times e to the 24/25 minus 8. But, of course, we take our calculator out, and we play around with that, and we get 28.563, etc., in which case, to the nearest tenth of a day, 28.9. All right, that's it. Pause the video now and copy down anything you might need to. All right, I'm going to clear out the text. Let's finish up the lesson. So today what we did is we reviewed some basics about exponentials and logs. One thing we reviewed about exponential expressions is assuming the base is a positive constant, there is no power that you can raise that positive constant to and get either a negative or 0. Again, no real numbers that you can. We also reviewed the method of common bases for solving exponential equations. Pretty simple, but elegant. If you can manipulate the two sides of the equation so that each expression has the same base, then you can set the powers equal. Finally, we really dove into logarithms. We dove into what they meant, how to evaluate them without a calculator, and how to solve equations that involved logarithms by using their exponential inverses. All right. Well, thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kurt Weiler, and until next time, keep thinking and keep solving problems.